Hello student, to the course of Foundation of Classical Electrodynamics. So, under module 2, today we will have lecture number 32 where we try to discuss about the electrostatic dipole. So, today we have class number 32. So, we will discuss the electric dipole. So, electric dipole is not a new term. So, the standard definition that we know, that if we have a 2 charge plus q and minus q and plus q separated by a distance d under the condition. So, that means system of two equal and opposite charge separated by a distance d under the condition that d is very small, tends to 0, then this is called the electric dipole. However, we will going to learn a more detailed discussion. We will do the more detailed discussion about the electric dipole and going to see that a system of charge distribution can also be considered to be a dipole, where the system of charge distribution having total charge q equal to 0. Suppose I have a charge distribution, some positive and some negative charges are there, and the total charge, if I calculate, is 0, but they have non-zero, they have non-zero dipole moment. So, this is important term, dipole moment. We will going to discuss this in detail. So, the point is, a system of charge distribution having total charge 0, but having non-zero dipole moment can also be considered as electric dipoles. So, dipole moment in discrete case, here in discrete case, the dipole moment P is charge multiplied by the separation. This is the way we define. So, this is my dipole moment. and in this continuous charge distribution the dipole moment is generally defined in this way. This is the r prime and rho r prime dv prime. This is the distribution of the charge for which I need to use the expression of the charge density, and this is the way we define the dipole moment. Okay, we will going to discuss in detail. So, first we will calculate in the classical way the potential and electric field due to a dipole. So, first we calculate. This is a very traditional calculation in most of the books you will find. So, we will first do that. So, potential and electric field due to dipole. This dipole structure, for example, are very important in, because in different branch of the physics we have this kind of structure where two opposite charges are separated by a distance d. So, small distance d. So, the knowledge of the dipole oriented thing is important. So, that is why we need to learn it carefully, because in other branch of the physics, not only electrostatic, there are a few other cases where this dipole are there. I mean this concept of dipole you will find very frequently. So, let us consider a coordinate system where two dimensional coordinate system, this is x axis, this is y axis, and two point q1 and q2 charge particular two charge point plus q and minus q are present here. So, suppose this is plus q and this is minus q over this x axis, and I want to find out the potential at some other point, say I want to find out the potential at any point over this xy plane, and that point may be P. Okay. So, the vector from the distance from Q to P in terms of vectorial notation, say this is R1 and this is curly R2. This is the position vector for the point P from the point Q1 and Q2, mind it. But I can also draw another line here which gives me the position of P in terms of the origin, from origin, and say this value is my R. Having an angle, say making an angle theta here. So, this is the structure, this is the standard structure. We know that we have a dipole here sitting over x axis and try to find out the potential at point P and how to calculate that. So, the potential for these two charge point is simply the, I can use the superposition rule. So, the potential phi at point P is simply potential that at point R, that is q divided by 4 pi epsilon 0, q is same for both the cases, and the distance is 1 by R1 minus 1 by R2. This minus sign because we have one negative charge and one positive charge, and accordingly the distance is R1 and R2. So, I write the potential in this way. Now, everything I like to write in terms of R, because here in the left hand side you can see this is a function of R. So, it is expected that whatever the result we have should be in form of R, because I measured the point where I like to find out the potential in this coordinate system where R is measuring from this origin. So, I can do that. So, R1 vector R1 is simply the R vector, and then if now in order to understand, in order to write properly, so I need to define the length between these two dipole, and that is d. D is the separation between these charge points. So, the R should be R1 should be minus of d by 2 and then x unit vector, and R2 in the similar way it should be R plus d by 2 x unit vector. This is R1 and R2. Now, I can calculate 1 by R1 and R2, but this is the magnitude. So, the magnitude of R1 simply comes up to be, because R I now know, R minus d by 2. So, magnitude of R1 simply R square plus d square divided by 4 minus 2 d by 2, then R, and the angle between these two, that is cos theta. This is a very standard way to write down the magnitude of a vector when we know the angle between these two vectors, the addition of these two vectors. And in the similar way, I can have the magnitude of R2, which is R square plus d square by 4, and then here we have plus 2 d by 2 R and cos theta. Okay. Now, R square I can write R1 square. So, this is square, otherwise I should put it to the power half. So, R square I can write in this way. The reason is very simple, that d is very less than R. So, I can write in the ratio of d by R to simply neglect that part, that we always do, and then minus of I take R square common, so it should be d divided by R and cos theta, and this the condition is R is very greater than d, because d is almost tends to 0, and I try to find out like a point dipole, this in compared to this point P, these two, d is very small. So, these two are like a point dipole present in the origin. So, R1 square can be approximated as simply R square. This term can be neglected. So, it is simply R square into 1 minus d by R and then cos theta, and 1 by R, because 1 by R is there in the equation. So, 1 by R1 is nearly equal to 1 by R. So, and then I should write 1 minus d by R and then cos theta whole to the power of minus half. Okay. So, now I can make a Taylor series expansion, make a binomial expansion, and d by R ratio is small. So, I can restrict up to first term, and that basically gives me this quantity, simply gives me 1 by R, and then it should be 1 plus, because it is a minus sign, 1 plus d by 2 R and cos theta. In a similar way, 1 by R2 will be simply 1 by R, and instead of having plus sign here we have minus sign by 2 R and cos theta. Okay. And finally, I need to calculate, because in the expression you will see that we have 1 minus R 1 minus 1 minus R 2, 1 by R 1 minus 1 by R 2. So, that quantity if I calculate here finally, so 1 divided by R 1, 1 divided by R 2, that quantity is nearly equal to d by R square and then cos theta, because I just subtract this from this, r will cancel out and d by 2r become d by r square and cos theta. So, the phi that I wanted to calculate at point r is simply comes out to be q divided by 4 pi epsilon 0, and then I have d of cos theta divided by r square. Now, this term I can write as per my convenience. So, I can write in a vectorial form, and vectorial form is, even though phi is scalar quantity, but right hand side this make use of this cos theta, and I can write q divided by 4 pi epsilon 0 and then d dot r divided by r cube. Now, d dot r gives us the value d cos theta r, and r cube is there. So, it will cancel out to make r square. Now, q d, this quantity I already defined, this is called the dipole moment p. So, my phi I can write in terms of the dipole moment, which is the important thing here, and eventually I get p dot r divided by 4 pi epsilon 0 r cube. So, at point r I know what is the potential due to the dipole, due to the electric dipole whose dipole moment p is known. So, that should be the expression of the potential of a dipole at point r. Well, now the next thing is to find out the electric field due to this dipole, because we starting point we write that potential and electric field. So, electric field you can readily calculate because potential is now known. So, my electric field E I can write simply by taking the minus of the gradient of this field phi r, and that is simply minus of 1 by 4 pi epsilon 0, because this term is constant, and then we need to make a gradient of this quantity dot r minus r cube. Now, this calculation I think I should give you as a homework, because this is a vector calculation and it will be a good exercise to find out. I can give you the hint. So, eventually whatever this term I am having here p dot r, this is a function of r and area. So, I should, so in principle I am having the gradient of two scalar field f and g, where f here is equivalent to say p dot r and g is equivalent to 1 divided by r cube. Now, the rest thing is straightforward, because you know how to deal with this expression. This is nothing but f gradient of g plus g gradient of f. So, you know what is your so the next step is to just find out what is p dot r. So, p dot r is simply p x x plus p y y plus p z z, and 1 by r cube is simply x square plus y square plus z square whole to the power 3 by 2. So, these two functional form you know, and then you just simply calculate exploiting this, you just simply calculate even in Cartesian coordinate you can calculate the value of E, and if you do that, then I am giving you the result, you should get a value like this. A straightforward calculation, that is why I should not do it, I keep it as a homework for you, but I believe you can able to do that. Then you will get this value P dot R and then R divided by R to the power 5 minus P divided by R cube. Please follow the standard way, and it will not going to take much time for you to calculate the E out of the potential that we calculated. Okay, the next thing I can also find out the potential in a interesting manner. So, that I am going to discuss here. So, first, in order to calculate that by exploiting the expression of the potential for continuous charge, this is the discrete way we calculate. So, the charge density for the dipole you need to calculate. So, now I calculate the charge density of the point dipole. Point electric dipole, mind it, I try to calculate the charge density here for two discrete charge, and we know, right. So, let me remind once again the how we calculate the charge density. Suppose I have a distribution of discrete charge, these are the discrete charge, it is distributed like this, these are the discrete charge Q1, Q2, Qk, and what was the charge density for that? If you remember, the charge density for this discrete charge system rho was defined like summation of Q, sorry, because I use a small q, so better I use small q, summation of small q k and then delta function r minus r k. That was the definition, that was the charge density for this all these discrete charges. And what is r k? R k is their position. So, that means this is one r and this is another r, and this is r k, this is r 1, r 2, r 3 and so on. So, these are the location of these point charges, and I calculate the density and it comes out to be like this. So, this is the same thing for dipole. For the dipole, if I want to calculate the density, charge density, so I can calculate, and suppose this is the point say plus q and this is minus q, and suppose we have a origin here and the distance from this point to the charge q, the and the point charge r is say r 0, and from here to here I have say d, the separation between these two, vector d. So, this vector comes out to be r 0 minus of d, right. This is the vector location for this point charge minus q. Now, my charge density for this system I can write like previously. So, this is the charge density of the system, dipole system. So, that should be a function of r, any point r, and in that is the the way I defined here, sum over this all the points. So, I have 2 points here. So, I simply have q and then the delta function of this location, that is r, and then minus r0, and then minus q and the location of the delta function. So, this is r and the location is r minus. So, minus of r0 plus d. This is the charge. Now, this is d is very small. So, I can make a Taylor series expansion here. D is small, tends to 0 almost. So, I can do that because delta function is a function. So, any function can be expanded in Taylor series. So, this function I will write simply r minus r0, but this one I can make a Taylor series expansion. So, the first around this point r minus r0, taking d is small. So, the first q I take common, so I should not write q here. So, this gives us delta r minus r0 first term, and what next? Then I have minus the derivative of this quantity multiplied by d. So, the derivative means here I have the divergence, the gradient of this delta function, and dot d, and so on. So, this is a Taylor series, I can go infinitely, but I do not need the higher order terms because d is very small. So, I should not go to a very large term because in the next term it will be d square, d cube, and so on. So, that is sufficient. So, I can see that these two terms will going to cancel out, and I have a relatively simpler expression, and that is under the condition that d is tends to 0, I do not require all this term. I simply have minus of q and d dot the divergence of this delta function at r minus r0. When d is very small, that means this quantity is very small, d is almost tends to 0. So, that means this q and q2 points are located almost at the position at r0. So, this is the position of the r0 become the position of the dipole, and based on that I can write an expression for the charge density for the dipole. So, this is the expression for charge density, but you can see carefully, one can see that this value is known, q multiplied by d is nothing but the dipole moment p. So, in dipole everything we write in terms of dipole moment. So, that is why I can write the charge density in terms of dipole moment, and it comes out to be minus of p dot the gradient of r minus r0. Okay. So, that we know. Now, the point is what we need to do and what we will do with this. I know that this is expression for the charge density for a dipole. Now, after that what we will do? So, we can calculate the potential in a tricky way. So, let me do that. So, the potential we have already calculated, and that thing we going to calculate once again. So, the potential that we calculate here is this quantity p dot r divided by. So, this is already calculated using the traditional way. So, we will going to use the expression of the potential directly, and that we know that calculation of the potential. I am doing the same thing here. So, the calculation of the potential here, you know, this potential at any point r is simply 1 divided by 4 pi epsilon 0, and if you know the charge density according to the Helmholtz theorem, I can write it, and for dipole it should be simply this. Okay. So, now this rho d I know, so that value is here. So, I will put it, and I can write it as minus of 1 by 4 pi epsilon 0, p is a constant. So, I can take it outside dot, and then after that we have this integration, and it suggests that it is integration, and this is over r. So, it over r prime, the operator should be primed, and then delta function r prime minus r 0 divided by r minus r prime and dv prime, okay, over the entire volume. Now, I make a trick here, because this operator is r prime. So, it is like I am going to use it like a chain rule, like this operator is essentially del, say del x, and if I make a prime, so that is del x prime in one dimension. I am just writing in one dimension. So, that means, and the function whatever I have, delta function is like x prime minus x 0. So, I can write this function as a whole y. So, del x prime is eventually del y, and if I now write in terms of this y 0, so del x 0 can be written as, okay, I can make it, okay, this del y using the chain rule. I can do that, del, say this is my function. So, I can do using the chain rule that it is over x 0 and del x 0 del y, but here y is x prime minus x 0. So, del y del x 0 is simply minus 1. So, this operator, if I now change in terms of r 0, then I should only have a minus 1. So, these things is minus of del f del x 0. So, whatever the operator we have in prime, that is equivalent to minus of 0. This 0 stand for this r 0, over that I am operating, and that is the trick here. If I do that step, my phi r will be simply p divided by 4 pi epsilon 0, and I can take this operator outside, because now this operator, so let me first write, because this negative sign is absorbed, and I have this operator over delta r prime minus r 0 divided by r minus r prime, sorry, not 0, r minus r prime and then dv prime. Now this is over r0 and entire integration is over prime. So I can take safely, I can take this operator outside the integral like this, and then my integral should be simply delta function r prime minus r0 divided by r minus r prime dv prime. Now this delta function associated with the integration over entire volume, this is a known value, right, and this value is simply 1 by 4 pi epsilon 0, and then we have over 0, and that quantity is the delta associated with delta, and I can execute this integral, and eventually I have 1 divided by, in place of r prime I will simply have in place of r prime I simply have r0. So it is r0, okay, and that is operator over operator r0. Now I can simply, so okay, one p is missing here, so I need to write a p here. So p is missing, yeah. So now these things again I go back to to write in terms of original operator r in the same way, and then again I replace back my previous negative sign, and it should be 4 pi epsilon 0, and then it should be the it should be the, here we have a dot sign because it is throughout it is a p dot that thing. So I have dot, then gradient of 1 by r minus r0. So this is precisely the value we had here. If I go back and check what is the potential I get, this is the value, because r divided by r cube you can execute by just making the divergence the gradient of 1 by r vector. So once you do that, you are going to get the same result. So this is another way to find out the potential of this dipole by exploiting the density of the system of dipole, charge density of the system of the dipole. So this is another way to just show that people can also do in this way. Okay, so we don't have much time today, our time is almost finished. So I like to conclude the class here. So see you in the next class, and in the next class we will extend more different thing related to dipole. We try to understand what happened if the dipole is placed some external electric field, what should be the energy, what should be the torque, etc. So thank you for your attention, and see you in the next class.